Hello everyone. Okay, second video. So, just a reminder, this is just a copy of what's in your reference, right? See where it says equilibrium? And so then if you, here's the first page, you turn to the back where it says equilibrium. So you have this information. So let's go over what we did in class to start off with. So the easy one is just remembering that pH plus POH will equal 14. Now, all of these equations, they are dependent, like this needs to be at 25 degrees Celsius, okay? So pH plus POH will only equal 14 when it's 25 degrees Celsius. And let's say that you don't have this memorized. Well, it's right here. pH plus POH is equal to 14. So now if you're given the pH, you can figure out the POH, or if you're given the POH, then you can figure out the pH. And the other part that we did in class is we went back and forth between having the concentration of hydronium H3O+, and then figuring out or calculating the pH. And then we did the opposite of that, where we had the concentration, we have the pH, and we were solving for the concentration. But a few things that I want to remind you. I want to remind you that anytime you have H3O+, you can just replace it with H+. That's completely fine, and that's also true in the reference here. So see how it says pH is equal to the negative log of that hydronium, the H3O+. You could just change it to pH is equal to the negative log of the concentration of H+. Notice what is missing. And what's missing on your reference is this equation right here. Okay? So you do need to know that if you are given the pH, you can solve for the concentration. And you do that by taking 10 and raising it to the negative pH, and that will equal your concentration of H+. Similarly, we have all of this with hydroxide, OH-. Like it's literally the same as H+ and pH. We just do the exact same thing with POH and OH-. So look at the similarities. pH and POH, they equal the negative log, and when it's pH, it's of the hydronium, H3O+, and when it's POH, then it's the negative log of OH-. This is something interesting. Often, the letter P in mathematics, they replace P with negative log. So if we think about this, pH, well, remember how P means negative log? And then H is the concentration of the H+. So pH is equal to the negative log of H+. Same with POH. Remember, P means negative log? And this time it's the negative log of OH, so it's going to be the concentration of that OH-. If we have more H+, it's acidic. If we have more OH-, then it's basic. Okay. You can also go between concentrations using this equation, but I'll tell you, often students don't. Like if a student has to go from here to here, I see them go this way, from the concentration of H+ to pH, and then POH. This is in your reference, though. It's kind of hidden. It's right there, but we don't have to use it, and we don't commonly use it. All right, let's see. I know we did some of these practice problems in class. Let's turn the page, go to page 12. Let's do some of these with the base. So remember how you had to memorize your big 6 strong acid? You also need to memorize the strong bases, but I think the strong bases are easier. A strong base is a group 1 or 2 metal. Okay, so a group 1 or 2 metal. Here's what I mean when I say a group 1 or 2. If you look at your reference, your green reference, this is group 1, this is group 2. So a strong base has a metal from either group 1 or group 2, and then we add the hydroxide to it. So if it's group 1, there's only one hydroxide, so NaOH. That's a strong base. But if it's group 2, like magnesium, then there's going to be 2 hydroxides with it. But they're both a strong base. Okay? And remember what I told you? For a strong acid, the concentration of the strong acid equals the concentration of H+. This is similar. The concentration of NaOH, because there's only one OH there, that equals the concentration of OH. But MgOH2, because this has 2 of the hydroxides, that means we get double the concentration of the OH minus. All right, let's do practice problem 10. Find the pOH of the 0.015 molar KOH. K is a group 1 metal, and it has hydroxide with it. So this guy is a strong base. And we know that when we have a strong base, whatever the concentration is of that strong base, see how there's only one hydroxide in there? So that's going to equal the concentration of the OH minus, and we know that that's 0.015 molar that was given to us. What we're solving for is the pOH. Okay? So we know the concentration of OH minus, and we're trying to go to pOH. Oh, so it's just going to be like one step to get there. pOH is equal to the negative log of the concentration of OH minus. Well, that concentration is 0.015. Okay, so if I take the negative log, oh, there's the natural log, there's log. Negative log of 0.015, that gives me a pOH of 1.8. pH and pOH, I'm sure we mentioned this in class, but pH and pOH are unitless. Concentrations is capital M molarity, or moles per liter, but pH and pOH are unitless quantities. All right. We will do, let's do one more together, and then we'll talk about water. So a solution has a pH of 4.25. Okay, so our pH is equal to 4.25. What is the concentration of hydroxide? So we're trying to figure out the concentration of hydroxide. So in this map here, we're given the pH, and we're trying to get to OH minus. To get to OH minus, we need to change this pH into pOH, right? So pOH is going to equal pH, or 14 minus the pH. Let's check my math, because we know that pH plus pOH equals 14. So then we would take that pH, we would subtract it to the other side. So yeah, 14 minus pH is equal to POH. All right, so 14 minus 4.25, that means that the POH is equal to 9.75. Great. Now that I have the POH, I can figure out the concentration of hydroxide. So I am solving for this concentration, but I've been given the POH. So the concentration of hydroxide, that's going to equal 10 raised to the negative POH, or for us, 10 raised to the negative 9.75. So our concentration is equal to 1.78 times 10 to the negative 10, and since this is a concentration, it's capital M molarity. So these were for acidic solutions and basic solutions, but we can also do calculations with neutral things, in this case, pure water, okay? So looking at page 13. All right, water is awesome and it's weird. So what I am about to show you, I'll distinguish if this is true for acids and bases or if this is only true for pure water. So here's the first thing that's only true. It might also happen, but not to an extent that's meaningful, but only in pure water, we might have a water molecule and
it's really good.
That's good. And this water molecule, as a liquid, it could break apart. Like sometimes water molecules just spontaneously could break apart into an H plus and an OH minus. Okay? And these are now ions that are floating amongst all the other water, so it'd be aqueous. That's fine, sis.
Thank you.
And then aqueous. So from this alone, so imagine all these different water molecules and a couple of them break apart and then a couple go back together and then a few others break apart. But what's cool is if we have one water molecule that breaks apart, then we get one H plus and one OH minus. And if there was 2, then it'd be 2, 2. And if there was 25, it'd be 25, 25. And so the amount of ions floating in the water, these are always going to equal each other, okay? Only in pure water, this is not true for acid and base solutions, only in pure water, the concentration of H plus will always equal the concentration of OH minus, okay? Now, this is where they always try to trick students. Just a heads up. Like, if you can remember this, it's going to help you so much. Let's think about this. What if I took the negative log of both sides, right? Like, what if I did the negative log of the H plus, and then this would equal the negative log of the OH minus? Well, negative log, well, that's just P, so this would be pH equals POH, okay? Again, only in pure water, the pH will always equal the POH. Now, if it's 25 degrees Celsius, then this is 7 and that is 7. But if it is not 25 degrees Celsius, then these are no longer 7. It could be higher, it could be lower. I'll explain how to tell in a little bit, but they will always equal each other. And that's usually how they try to trick students. They increase the temperature or they decrease the temperature, and you have to realize that these still equal each other if it's pure water. Well, okay, great. Let's talk about that. If let's say it's the temperature increases. So like let's say we increase temperature. If you increase the temperature, that's going to cause more of these water molecules to break apart. So if there's more water molecules breaking apart, there's more of this guy, there's more of that guy, right? You could say if the temperature increases, we increase the concentration of H+. We also increase the concentration of OH minus. All right, great. But if you do the negative log, that equals pH. Remember how concentration and like the P value is always inversely proportional. Like the more H plus we get, the lower our pH is going to be. And the more OH minus we get, the lower our POH is going to be. So in pure water, if the temperature increases, the amount of H plus and OH minus go up, and the pH and the POH go down, and these two things equal each other. And these two things equal each other. And we could write this all again just with opposite arrows, like if the temperature decreases, then that would decrease the amount of H plus. That would decrease the amount of OH minus, which would make the pH increase and the POH increase. Okay, now, there's something I'm going to show you that will make more sense when we get into our kinetics unit. But I just need you to know, and it's on your blue reference. KW is just a number, and if it's 25 degrees Celsius, then this is that number. This is what KW is for pure water. But KW, which is a constant at certain temperatures, it changes if the temperature changes. But KW will always equal concentration of H plus multiplied by the concentration of OH minus. Okay, it doesn't matter what the temperature is, this is always true. But wait, isn't H plus and OH minus, they equal each other. So couldn't I write this KW is equal to H plus multiplied by H plus? And isn't that the same as KW equals the concentration of H plus squared? So let's say you're given KW, how would we figure out the concentration of H plus? Let's take the square root of both sides. The square root of KW will equal the concentration of H plus. And then reminder, the concentration of H plus will always equal the concentration of OH minus. Okay. This is the other thing. I'm going to put a box around this one. Maybe a star too. The three things that have stars are what I really need you to remember about pH and POH of pure water. That doesn't matter what the temperature is, the concentration of H plus always equals the concentration of OH minus, which means it's always neutral. pH always equals POH. If it's 25 degrees Celsius, then the pH is 7 and the POH is 7. If the temperature is higher, then the pH and the POH go down. If the temperature is lower, then the pH and the POH go up, but they still equal each other. And then I need you to remember that if you take the square root of this KW, it's going to be a number that they give you. If you take the square root of it, that will equal the concentration of H plus, which is also equal to the concentration of OH minus. So, first one, find the POH of pure water at 25 degrees Celsius. Well, if it's 25 degrees Celsius, the pH and the POH equals 7, because we know that pH plus POH has to equal 14, at 25 degrees Celsius. So if they both equal 7, then it adds to 14. Now, look at this next one. Which of the following accounts for the observation that pH of pure water at 35 degrees Celsius is less than 7? It's 6.8. All right, let's remind ourselves. If we see a temperature increase, that means that more of the water molecules are breaking apart, so we'd get an increase in the amount of H+. And then if you turn it into a p-value, like a pH, it's always going to be the opposite. So if we increase H+, that means we're decreasing our pH. So let's look at the different answer options and see what we think. At 37 degrees Celsius, water is naturally acidic. This is the most commonly chosen wrong answer. We want to say that it's acidic because the pH is less than 7, and isn't that acidic? Yes, it is if it's 25 degrees Celsius. But guess what? For 37 degrees Celsius, neutral is 6.8 because the amount of H+ and OH-, they equal each other when it's neutral, and this is always true in pure water, and so then the pH will always equal the pOH. So both the pH is 6.8 and the pOH is 6.8. It's not acidic, it's neutral because it's water. At 35 degrees Celsius, the auto-ionization constant for water, Kw, is larger than it is at 25 degrees Celsius. Ooh, auto-ionization. Okay, this is what I would do. I'm going to explain it, but I would say I don't know enough information to say that B is wrong, so we'll come back. At 37 degrees Celsius, water has lower density than it does at 25 degrees Celsius, therefore the concentration of H+ is greater. Density wouldn't change the amount of H+. At 37 degrees Celsius, water ionized to a lesser extent. That's the opposite of what we said. We said when the temperature increases, then more of them break apart or ionize, become ions. And so that would mean that we'd increase in how much is ionized in that H+. And this says it's lesser. It says it decreases. So D's not true. Correct answer is B. Now let's think about this for a second. Remember how I told you if the temperature increases, we increase in the amount of H+, and that would also mean we increase the amount of OH-. Well, look at what Kw equals. It's H+ multiplied by OH-. So if these numbers get bigger, then Kw gets bigger. If these numbers get smaller, Kw gets smaller. So yeah, when the temperature is higher, then Kw is larger. Okay? We're going to get lots of practice with this in class because water is cool, but it's really weird, and they like to give you problems where the temperature is not 25 degrees Celsius. So don't forget that no matter what the temperature is, if it's pure water, H+ always equals OH-, pH always equals pOH. And if they give you Kw, like they give you the number for Kw, you just take the square root of it, and that will equal the amount or the concentration of H+, which will equal the amount or the concentration of OH-. All right, everyone, good work. We will see you in class.